Yes. Hi all, thanks a lot for the organizer for inviting me. The first time in India, and it's very nice. I'm thankful. So first, I'd like to my talk title is Many Body Quantum Chaos, Spectral Form Factor, and Ginibre Ensemble, which is one of the simplest non-Hermitian random matrices. So first, I would like to thank my collaborators, John Chalker, Andrea De Luca, David Hughes, Salmi Shafam, Tamaj Prosen, and Jiajin Li. And Salmia is graduating soon. Jiajin may be graduating soon. Also, there are other collaborators here. Our big goal is to find universal signature of quantum chaos beyond those described by random matrix theory in the presence of many body interaction. So the punchline of the talk today is that we're going to claim that in many body quantum chaotic systems, in generic ones, we already know that in time, these Gaussian ensembles emerge. So these are GUEs or CUEs. And we are claiming that if there's notion of space, and if it's a many body systems with strong interaction, Ginibre ensembles also emerge. So you guys are experts also in these kind of things, but I'll take a few slides to talk about this. So what's the notion of quantum chaos? So the consensus, current consensus, is to use spectral statistics and to use eigenstate correlations to probe quantum chaos. This spectral statistics is the most basic one. So given a Hamiltonian or a circuit or a unitary evolution operator, you can diagonalize it. Having the spectrum, you can compute all the gaps. If you have the gaps, you can plot the distributions of these gaps. And if the distributions of the gaps of your systems coincide with the distributions given in random matrix theory, then you say that the system is quantum chaotic. So this is the content of the BGS conjecture. This random matrix theory distributions is called Wigner-Dyson distribution. And in particular, when the gap is 0, you see that there's no probability of finding any pairs of gaps with gap 0. So this is called level repulsion. If instead we're in integrable systems or MBL systems or other systems where there are lots of conserved quantities such that the spectrum is not correlated, then you'll display another kinds of distributions called Poisson distributions, as if the levels are not correlating. So one slide on random matrix theory. So random matrix theory is a theory about ensemble of random matrices. These random matrices are chosen to be really simple, such that it's analytically tractable. The advantage is that it captures certain universality of chaos, and that includes in many areas, including nuclear physics, number theory, and all that. And one of the big applications is chaos. To be more specific, one would write the probability density of a matrix, random matrix M, to be exponentiations of a trace of M dagger M. If you expand this out, you will see that that just means that each matrix element would distribute in a Gaussian distribution. Furthermore, you can impose a second condition with hermeticity. With these two conditions, you can define several ensembles. The simplest one would be the so-called GUE, Gaussian unitary ensemble. That is to impose condition 1 and 2. This gives you an ensemble of Hermitians H, we can call it, and it's often used to model Hamiltonian. If there's another set of closely related ensemble, which is defined by having a Haar measure, so-called, on a unitary group of matrix size n. So you can think of these Haar measure, these Haar random unitaries as rotations on the Bloch sphere, where each rotation is randomly drawn, and any rotations is as likely to be drawn as any other rotations. So these would give you a set of unitaries, U, and this is often used to model time evolution of chaotic systems. Another ensemble that is perhaps not as familiar is to apply only condition 1. So in this case, we're not applying any hermeticity, and these would simply be matrices with matrix elements that are Gaussianly distributed. So this is one of the simplest random matrices out there. And we'll see how this emerged from many body quantum chaotic systems. Okay, so chaos have been here for a long time, but there is a revival in 2017. Credit to Nahum, and there are many great papers by Nahum and their teams. There's a new class of model, which are called random quantum circuits, which Austin also have taught us nicely. This models combines the power of random matrix theory and locality. So if we have this space-time diagram, time going upwards, space going horizontally, each line you can consider as a world line of certain particles. For us, we'll put them in a lattice, and these can be spinned. So we will parameterize it with Q levels. So when Q equals 2, this are spin half particles going up and down. As time goes on, you would allow different world lines to interact locally in a brick wall geometry. These are chosen from the CUE that we described just now. These are Haar random unitaries. And the most studied kind of the circuit that are most studied are the ones where there randomness both in space and randomness in time. So each of these gates, we consider a big ensemble. Each realization of them, each of these gates are randomly drawn, both in space and in time. There's a problem about, there's something not ideal about this, namely that we do not have a spectrum. So in order to have a spectrum and to have eigenstates to study, we study instead a flow K random quantum circuits. These are the spectrum. The only difference here is that in time, we're going to repeatedly act the same gate over and over again. So in contrast to many other talks where we study some flow K systems for the new physics that flow K system give, we really use it as a tool to understand even time independent Hamiltonian. We realize that using a flow K unitaries like this actually gives us some some tools to simplify the problem. So these are the two big motivations of using flow K random quantum circuits. One is spectral statistics, which I will talk about today, and also eigenstate correlations. So this we can discuss offline more if you're interested in this. And this in particular will give us something beyond the usual contents that's given us from ETH. Okay, so a quick introduction of spectral form factor. If given a density of states, this is rho of E, is a sum of many delta functions, E minus En, where En is the spectrum. You can probe this object here. This object is just a two-level correlation function. This is asking what's the probability of finding two levels with distance omega. This left bracket and right bracket denotes an ensemble average, as we're thinking an ensemble set of realizations. If we Fourier transform this object, we'll get K of T. These delta functions will be brought up to the exponents, and we can see that this is a double sum of phases of eigenvalues. This is actually a natural way of probing energy level. Another way of writing this is just if we're thinking about unitary dynamics or some Hamiltonians, you can write it like this. Each trace would just correspond to a sum over eigenvalues. So why do we want to study this? This is simple, basic, and it captures certain feature of universality. This probes, second reason is that this probes energy correlations that are long range, as opposed to these short range nearest neighbor spacings that is probed in early days. In particular, we will show that the many body side of quantum chaos is going to show up with some universal signature in longer range energy correlation. This is also experimentally measurable. This Solar's company has a few proposal, and there will be experimental results gonna go out to archive soon as well. This gives rise to many recent activities in theoretical physics, including the discovery that these black holes can be modeled by random matrices by Kotler et al. In 2017. Many body quantum chaos, which is the focus of this talk. And also, this has one of the earlier papers discussing this MBL to thermalization transitions also use these SFF. Great. So these are just a flash of these paper. Black hole random matrices, onset of random matrix theory, behavior in chaotic systems, semi-classical RAM with SYK. So black hole people often focus on the model SYK, and certain aspect of SFF can be studied analytically. And back then, there are two parallel teams computing SFF. We have one of the teams using these random quantum circuits. The other team would be focused on those models that Austin described, those dual unitary models. Okay. And these are the experimental experimental proposals so far. Okay, great. To know the most basic behavior of SFF, one consider the simplest ensemble, and we'll select the CUE that we described. So these are just ensembles of unitary matrices. So SFF is given here, plotting K in the y-axis, x-axis we plot T. We see that as T increase, K just increase as T until it hits a plateau at a time that is of order n, where n is the matrix size. So this n can also be thought of as the inverse of the mean level spacing. So if you look at this quantity here, this is saying that when T is very large, when T is so large that's larger even than the mean level spacing, this object here would just turns into delta m and n point averaging. So this delta would kill one of the sum, and the leftover would be n. So this is saying that this quantity, if you're probing a distance so small, smaller than the mean level spacing, this would simply be a flat line. And okay, so this is the canonical behavior. This is the reference behavior that we will compare to. If your system has behavior that looks like this, then we say that your system is behaving like random matrix theory, and therefore we call that chaos. This kink here, to refer to the earlier part of the talk where we mentioned this nearest neighboring spacing, that is probing a scale that is of mean level spacing, and hence it's also correspondingly is probing the physics around here. Now we're using this quantity, we're able to probe something that's much earlier. If you instead don't have a chaotic system, not for CUE, but for some Poissonian spectrum, then K simply goes to a flat line very quickly. First result is SFF in generic many-body quantum chaotic systems based on these papers. Okay, so I'll introduce a heuristic. To consider many-body quantum systems, it's convenient to first think about different limits. The fully coupled limits would have, you can think of the system just evolving just as one big CUE, and the spectral form factor behavior would just be a linear line going to a plateau, just like the CUE behavior we showed just now. The other limit would be a completely uncoupled limit, where each site evolve in time with an independent CUE. Each CUE would give you a factor of T, and spectral form factor would simply be going as a product of T, so T to the power of L, until it hits a plateau, which would not be explained in that approach. It's due to some non-perturbative behavior. But importantly, this timescale, the timescale where it hits a plateau, is now independent of L. So a heuristic, a very loose argument is to say that if I have systems and the systems are initially not coupled, and you let it evolve in a many-body quantum chaotic systems, different spins that are far apart would not have time to talk to each other yet. So in early time, you would expect it to behave more like the bottom case instead of a top case. And eventually in late time, it's going to behave something like a top case. So the simplest way is to just interpolate between the two behavior. Earlier time, perhaps it goes like this upwards. Late time, it goes like this. Then we'll perhaps have this picture. So we have an early time increase, and then late time, you have this ramp. So we call this a bump ramp plateau behavior. But the argument I just gave you is a loose argument, because spectral form factor is really a trace of U, and you shouldn't just consider one initial states that are uncoupled evolving. Yes, please. Here, so So I'll show you numerics that wouldn't rely on that assumption, but the analytic solutions I'll give you would rely on large Q, except for the result 3 that I'll give you, which would be okay with finite Q. But this behavior does not, will still be there with finite Q. This behavior of this guy. Right, so that would be a model dependent question, whether that model is in finite Q is chaotic or not. If it's sufficiently large, it should be okay. Yeah. Okay, so given this picture, I would like to view it in this parameter space that we'll refer to quite a few times. So in here, we are kind of doing a finite L. So let's say L is 17, and then we evolve upward in time. We first experience a bump here, this region, and then we experience this ramp, and then we experience this plateau. And there will be these lines separating different regimes, T Heisenberg. And this time scale that we introduce now is called T Thouless. So T Thouless currently is just defined as the time after which the connected part of the spectral form factor behaves like the random matrix theory behavior. I should mention that this connected part, many people in the field have computed SFF also with the disconnected part, and there can be, the density of states can introduce some other signals that are not universal that could hide this universal behavior in the early time. Okay, so our claim is that SFF bump ramp plateau behavior is a signature of many body quantum chaos with emphasis on many body. So, okay. Feel free to ask any questions. This on the left, I'm plotting, this is my drawing, but this is to illustrate a connected part. So disconnected, with disconnected part, typically you would have something here if your density of states have an edge. So for a typical Hamiltonian system, for instance. Exactly, that's because I'm illustrating the connected part. So let's go, okay, so here I'll just give you the numerics. So first I'll give you 2 examples of unitary circuit where the density of states is flat. So there wouldn't be what we're concerned about right now. It would just be this bump. So here, K and T, and increasing system size. So as you increase in system size with this normalization, you will see that this bump, importantly, this Thouless timescale is increasing in L. So there's a big region here where there are new physics about the many-body interaction. This is another model. These are two different models. Those are just quantum circuits model and chaotic quantum circuit models. The details don't matter so much here. Another one would be this paper, which is the famous chaos challenge localization paper, where they simulate some XXZ model. And you can see that the right-hand side is the SFF without minusing the disconnected part. And you will see this is the oscillation I think you were talking about here in the beginning. And this one would be the connected part. Okay. And we care about the connected part. This would be another, just to illustrate, this would be some driven Bose-Hubbard model. And this bump would also show up. Great. So first I will show an analytical result that we first found in 2018. And we show that, we demonstrate that it's universal in this paper, in this Nature Communication paper in 2022. So this is one random phase model. I wouldn't go into the details of how we calculate the analytics. This is just to be concrete here. So these quantum circuits would be 2-layer. The first layer would be of this CUEs, independent CUE for each site. And these are just one site rotation here. In the second layer, we will have random phases. These random phases are chosen to be simple so that we can do analytical calculations. And in particular, to be specific, you have 2 colors or spins coming in. This spins, again, has Q degrees of freedom. And these are diagonal. So there's a delta AC, and there's a delta BD. And depending on the input color or spin, we're going to assign it a random phase. And these random phases are Gaussian. These are controlled by these parameter epsilon. So there are 2 parameters in this model, Q and epsilon. Okay, so I'll give you directly the analytical solutions for this first analytical solutions for this bump ramp plateau behavior. So here we're using this large Q approximation. So if we send this model to large Q, again, this is the on-site dimension sent to large, the spectral form factor can be mapped to a classical model. That's quite interesting. So on the left, you can think of this as a one-dimensional quantum circuit. On the right, you can think of it as a one-dimensional classical model where each site has T states. And the classical model is a Potts model. The Potts interaction is given such that if site 1 and site 2 have the same degrees of freedom, one out of T of them, then there's no cost. If they're different, then there's a cost that is proportional to e to the negative T. So this is a ferromagnetic model because and with the interaction strength proportional, beta J is proportional to epsilon T. So this is a result. In fact, this result actually applies to all dimension, although I'm illustrating with 1D. So let's try to interpret this result. When T is very large, so late time, this interaction just force everything to be a ferromagnet. So each site has to take the same state. And you would just have T states here. And this actually gives rise to the RAM T. So currently, this is quite peculiar because we're studying a Potts model where the number of states is increasing in time. Okay, so this is large time behavior. In early time, instead, this is almost comparable with 1. Then you would be in this paramagnetic phase for this Potts model, and all these configurations with different colors would contribute to K, and it gives a higher rise. If you go from large T gradually to smaller T, eventually you will hit this, the interaction will be weak enough to allow these domain wall states to contribute. And these are the picture we have. So our picture is that as time goes on, the systems, different part of the systems would occupy these kind of states, and eventually they would all go together with this classical Potts model. For people who are more interested in the details, you can actually think of this K as 2 periodic orbit. So one of the periodic orbit would be given by this black circle here. The other would be given on the other side. And the averaging or chaos essentially is telling you that on each site, these T states would correspond to different diagrams. Sorry, I should also mention these black dots are the unitary U, and this is for T equals 3. And the white dot would be for U star or U dagger. The fact that the models are chaos is saying that on each site, these T state Potts model, where the T states are these ladder diagram, okay, which I wouldn't go further into the details, but I can talk about this offline. Okay, and these are often called local pairing of Feynman diagrams, Feynman histories. So this also connects to different talks that we listen to, including this return probability, and those objects that both have pairs of U and U dagger, and it talks about two pieces of systems evolving, and their phases going to interact. So these are all these U and U daggers are connected. Okay, so that's result 1. Okay, so to check whether these results are universal, we would look in this regime diagram again. So we will have to go to thermodynamic limits to test whether these results are universal. If you go to this direction, all the systems would give you just a ramp, so that's a bit boring. You can also go for fixed time and go to large L. There's another regime, the bump regime, which we have other papers discussing it, called spectral Lyapunov exponents. We can characterize it with some exponential increase. But the interesting scaling limit we claim is the so-called Thouless scaling limit. So we scale the time in T and L in such a way such that we are following this line, and we send everything to infinity. So specifically, this scaling limit is to say that L and T goes to infinity, and for each time Thouless, I'm defining L Thouless. So time Thouless, you give me an L, I give you a time Thouless. For L Thouless, you give me a T, I give you a L Thouless, the inverse function. We go to the thermodynamic limit while keeping L divided by L Thouless fixed. In that limit, we can use the solutions we have just now to compute the right-hand side of spectral form factor to get a scaling function as a function of this x. And on the right, we test this by testing two models here. And we see that the data fits nicely onto the green line, which is the analytical solution in large Q. So we're testing large Q with finite Q numerical data. So in the big picture is that we claim that there will be universality class depending on symmetries and dimensionality. So in many, yes. That's the, oh, okay, yes. So you figure just the inverse function of Thouless. So here in numerics, this would not generally be a universal function. So each models would be model dependent. And we actually don't claim that these functions to be universal, but the behavior. So this line here may curve different ways depending on the model, but the symmetry is important. And then we just say that you send this model to this limit here and compare the approach of K across this area. And so there's one parameter for each model where you rescale, where you collapse them together. Yeah, and that is, but you only need that parameter to collapse them together. So result 2 would be spectral form factor for non-Hermitian matrices. I think this, yeah, please. So this approach is, the plateau is non-perturbative. So this approach I'm telling you is actually perturbative in 1 over Q. So I was just about to say, because we're using large Q. So the RAM part actually starts in T Heisenberg, where it is proportional to Q to the power L. So the plateau is actually infinite currently. It's simply that this approach, in large Q, there will be no plateau. Yes. So in finite Q, we'll need more techniques to probe that. Okay. Any more questions? So the second results I'll present is, there's just 4 slides here, I think, around. It's SFF for non-Hermitian matrices. And this may be of interest for several of us because of open many body system. So there are several attempts before, a few years before, for people trying to apply SFF for non-Hermitian systems, to apply to analyze spectrum of Lindblad and Krauss operator, etc. But there is a problem here. For non-Hermitian system, generically, we will have complex eigenvalues. And these eigenvalues would have a real part and a complex part. If you substitute this back to the definition of SFF, this IY would create just an exponential factor. It would ruin the good properties of summing over all exponential factor phases. So instead, the insight is to treat these eigenvalues of non-Hermitian matrices as 2D gas. And the idea is to just study the correlations of these particles in this gas. So we will write a density of states. Now the density of states is parameterized by 2 coordinates instead of 1 in the Hermitian case. So you parameterize with x and y, and you have this energy difference, omega, or distance, and omega prime. And we Fourier transform this. And this would be the natural definitions of spectral form factor for open quantum systems and for non-Hermitian matrices. So here it will also be convenient to define a complex time, tau, and there will be polar coordinates here. Okay. So to understand this, again, we will go to the simplest non-Hermitian, simplest random matrix ensemble. And that would be the so-called Ginibre ensemble that we have been talking about. We find the analytical solutions for this Ginibre ensemble, sometimes also referred to as GinUE. And that solution would be comparable to in the Hermitian case, the GUE solution for SFF. But this is the Ginibre solution for DSFF. We call this dissipative spectral form factor. So here we plot the solution in orange. This is the connected dissipative spectral form factor. It reached a plateau of n, like the GUE case, but it has the approach is given by a Gaussian function. Okay. Interestingly, so this function here does not depend on theta but only on mod tau. Okay. So there's a rotational symmetry in this parameter space. It increases if n is very large. You can expand the exponential and see that the increase the ramp is actually a quadratic ramp as opposed to linear ramp in Hermitian case. And that's one big contrast. And the other, if you don't have a chaotic system, chaotic non-Hermitian matrices, then you can model it by Poisson distributed random eigenlevels in a 2D plane, and you just get a flat line. This is also similar to the Hermitian case. So to test this, one of the first tests we did is just to test it a zero-dimensional system that has chaotic phase and an integrable or non-chaotic phase. Here, this would just be a cake top, zero-dimensional cake top with J. The model really doesn't matter so much. You can construct some jump operator, and this Krauss operator, you can analyze it in the super operators as a super operator, and you see that in the chaotic phase, it follows this G-nu-E solution, and in the non-chaotic case, integrable case, it follows this flat line. So the claim is similar. There will be a corresponding BGS conjecture for non-Hermitian systems where we say that your system is quantum chaotic or chaotic if this DSFF coincides with the Ginibre. Okay. Note that people previously have studied the nearest neighbor spacing of this non-Hermitian matrices. Just that currently we're saying that this object naturally arises to study long-range one. Yes, go ahead. Why is it non-Hermitian? Because of the Krauss operator. Because we introduced this Krauss operator. So the operator will be you have this evolution defined by this H, and then we have this K1, K2, K3 Krauss operator. And then we study the super operator for this instance. But you can apply it to any open systems that you want. Yes, but not just top line with this case. So okay, I didn't write the equation here, but the usual thing you. Sorry. That's not what I'm talking. If you go to the basic level, it's just say that if you give me a non-Hermitian matrix, we have a recipe of detecting whether it's RMT-like or not. So we the full channel. This is a full channel, not. Yes. So I'm evolving something like this. Sum over alpha, and I folded through the super operator study spectrum. Yeah. So I should have written it down. But we on a paper that will hopefully be out soon, we have a numerical survey of different open many-body systems with spatial extendedness, and we see that for all the cases that you generically expect them to be chaotic or sufficiently generic, it follows this structure, and the long-range correlation, even in the non-Hermitian systems, will tell you something more. And if it's spatially extended, then there will be some kind of deviation in small tau. Okay. So finally, I'll give you the third result, which is how Ginibre ensemble emerge from the system. Okay. So here we'll first start talking about translation invariant system, but the results would actually generalize to non-translation invariant system. Consider this circuit. You can have circuits that does not have temporal periodicity, does not have spatial translation invariance. These would be the circuits actually most studied in the field. You can have flow case systems without translation invariant, but you can also have flow case system, a non-flow case system, but with translation invariance. This is actually the simplest toy model you can study. And you can also study this deterministic model. Okay. So with this, we focus on this case. With this case, you actually can define, because of translation invariant, you can define a flow K operator in space direction. And that would be saying that previously we have been studying this flow cape operator in time direction, but now we can study the flow cape operator in space direction. So these appear previously quite a bit, the space-time duality idea, including the dual unitaries that was mentioned. Okay. So this heuristic argument is perhaps quite convincing to me. So now you can write a spectral form factor. Previously, you write it in terms of the flow cape operator in time, but now you can also write it as a flow cape operator in space, which we call phi. This phi has a spectrum set that has a real part and an imaginary part, and the real part generically is not 1. And if you expand it, plug it in with the double sum, you have the diagonal term and the off-diagonal term. The diagonal term is purely positive. So if you say that you hand-wave, do the most hand-waving argument and say that perhaps a point ensemble averaging, which I denote now as the bar, this second term vanish, that cannot be, because the first term is exponentially increasing. So just to be clear, here we have this system here. For fixed time, we'll have a fixed dual system, dual flow cape operator. And as we increase L, we are stacking these dual systems in space. So this is like going in the regime diagram to the right. And the fact that, okay, there exists, you will first go through the RAM regime, which is linear in L, and then you explode eventually to exponentially. So the fact that there exists this RAM regime for chaotic system, generic chaotic systems, means that actually the second term cannot vanish. So there's universality in this regime diagram behavior. So we're asking whether there are universalities in these kind of spectral correlations of these guys. So now we'll investigate the spectral correlations of these spectrum here. So if you do the investigation, plugging in the eigenvalues of phi, investigating a correlation, you'll see that it fits. Investigating the DSFF of the systems, you will see that it shows the behavior of random matrix theory, i.e., this dual spectral correlations falls under the Ginibre universality class, in particular displays level repulsion. Okay, and we tested for all kinds of systems, I think maybe 5 or 6 kind of circuits, including with temporal randomness and also flow K and translational invariant. So these are all different systems, and this is inset is just the nearest neighboring space. So in the last few minutes, I'll say how we can actually use this fact that can be modeled by Ginibre to model this universal behavior of many body quantum chaos. So with this, we have this phi here, this dual flow K operator, and you can replace each one of them with Ginibre matrices here. So that's the step we do, and this is what we're saying. So in large time, these kind of circuits behave like COE, and we're saying that in large space, these circuits behave like a chain of Ginibre ensemble in space. And this is just some math, but we can compute. So we compute spectral form factor on the left-hand side. We can also compute spectral form factor on the right-hand side and use it to model the left-hand side. So we now computed spectral form factor on the right-hand side, and we will get a solution for spectral form factor for the Ginibre ensemble, Ginibre matrices, Ginibre ensemble, denoted in G. What we see is that there's some analytical solution. These analytical solutions would have a large N expansion. So if we plot the corresponding regime diagram for this analytical solution, we see that it has a RAM regime and then a regime that explodes in L. This is very interesting. This is very tempting because it compares with, it can be compared with the case in the many body quantum chaotic case. What we do is that we compare it, and just like in the many body quantum chaotic systems, we send it to the Thouless limit to check the unit, to go to a limit where universal features are being captured. We go to a Ginibre case, and we also go to the corresponding analogous Thouless scaling limit, and to find out the scaling form for each side, and the conjecture is to say that they are the same. Lastly, we compare them, and we show that the green line would be the Ginibre ensemble predictions, and the colored dots would be the 2 circuit models that we test out. And you can see that in the inset, we're actually plotting the this Thouless time or Thouless length, and we see that they don't scale the same way, but it's the scaling form that are universal. So we are saying that at the Thouless limit, these two are the same, and we have an analytical form for this. So I'll give some remark. So the remark just now, I said Thouless length is not universal. The other, sorry, just a few more minutes. The other remark is that this is the first finite Q results that we can model generic quantum chaos. Previously, the results are all using large Q approximation. And the last two slides would just be saying to say that we can generalize this. I won't go into the details by constructing Ginibre ensembles that respect the respective symmetries. So if you go to case, we call case B and D, we have flow K. It means that in the dual space, there is temporal random, so that there are dual translational invariants. And you could construct a corresponding Ginibre ensemble. And we can actually recover result 1 in the first part of the talk, where there's Potts model. But of course, this is, you can say that it's a priori because we're just constructing it and matching it. But we believe that that's a natural way to do it. Okay, and we also fit it for this case, B, C, D will have corresponding numerics checking them. Great. And in the last slide, I just want to emphasize that because of many body quantum chaos, we have this new regime here where there's a bump. Without this bump, we actually would not be able to, there's nothing for the Ginibre ensemble to model. So this Ginibre ensemble is emerging when we have many body quantum chaos, when we have many body interactions. And there are other interesting facts. Another fact is that we have Ginibre ensemble. We're saying that if we have CUE circuit made of CUE, we rotate it, it looks like Ginibre ensemble as we increase in size. If we have a Ginibre circuit and we rotate it, this is still Ginibre. So the Ginibre circuit is an emergent object there that, and it has to fail at some point. So these are all very interesting things. And we're currently doing different kind of symmetry class using Ginibre ensemble to see if we can comment on other objects and different symmetry. Yeah, okay, different symmetry class. Great. Thanks for your attention. Feel free to ask any questions.
So is there any sense that, so in the last slide that you were showing about this
yes.
many body interactions required for this Ginibre,
yes.
So there is no dissipation in this system, right?
There's no dissipation in this many body quantum chaotic system. So
so in the sense that it seems that interactions could be a proxy for dissipation. It's almost like, for example, you have seen this in time crystals also, like it's either for dissipation or interactions.
And also, I think Fatica's team also were interested in, also Tarun's, Grover's team were also interested in the non-unitary dynamics in the space direction and studying the reverse. But here, our motivation would be to study the usual time direction and try to find methods to probe the time direction. But people legitimately do study whether you can consider the space direction as a non-Hermitian open system. But here, it's not obvious for us whether there's an open system associated to each closed system. But we definitely are thinking about there's a closed system, dual direction symmetry class associated with each time direction symmetry class.
Have any intuition if the kind of interactions that you need for that to happen, or it should be like, it doesn't matter what interactions?
I don't have a lot to say except that it would be chaotic because of just simply because of the dual direction is chaos. So it's not going to be something that is open system that are integrable. And yes, so it's very interesting whether there could be structure. What's the structure in the dual directions? We study different symmetry class in, let's say, set 2. The dual would be another symmetry class in set 2, et cetera, et cetera. So those are quite interesting, and we are working on it right now.
Thank you.
Other questions? So I have a small question. Sorry.
Yes.
So if I'm choosing from the Ginibre ensemble, there's no reason for me to choose n by n matrices, right? So in principle, I could choose n by m matrices.
Okay.
Matrices Z, and then do Z dagger, and I get back n by n matrices which are in Ginibre ensemble, but they have a different symmetry. So does this play a role in your study?
So we have not tried diagonalizing n by n, but then in fact, you can say given a system in T, the dual system is QT, Q to the power of T. What matrices size you use to model this the dual system. So it turns out that you could have defined an effective system size, which is the log of you have an effective time for the dual unitary, or you just exponential q to the t. You can say n is q to the t, but actually that wouldn't be directly modeling this each dual circuit because they scale differently. This boundary here scales differently for each cases. We're really claiming that only in the scaling limit they model each other. So for each fixed system size, a fixed n Ginibre is not going to necessarily model a fixed q to the t circuit.
But I think Karol Juchkowski actually pointed out that these ensembles have different symmetries. And so they have interesting symmetries. Maybe this is of interest.
Yes, that's exactly what one of the things we're doing right now. So there are more symmetry classes. Maybe you're saying that there are more symmetry classes in the non-Hermitian case, and you wonder there are fewer symmetry classes in the time direction in the closed system case. So maybe there's a one-to-many map here. It's not going to be one-to-one. So how this structure goes is quite interesting.
The underlying point was different. It was about modeling probability distributions of density matrices.
Yes, there is a Japanese readers group was studying different statistics for different classes, and many of them actually coincide together. But that's I can tell you guys more.
Other questions? Okay, if not, let's thank Amos again for his wonderful talk.